Okay, I hope I'm audible to all students who are attending this lecture of Mathematical Methods for Economics, Part 2. We intend to start with a new topic in our MME2 course. This is constraint optimization. Okay, formally, this is chapter 18 of the book I prefer to follow for the MME2 course, which is Sydsaeter and Hammond. The fourth edition of this book. Okay, so let's start with our lectures on constraint optimization. So first we look at two variables and one equality constraint. Two variables and one equality constraint. So let us look at the optimization problem involving two variables and one equality constant. Okay, so consider the problem of maximizing, or for that matter I can write minimizing, a function f of xy when x and y are restricted to satisfy the constraint g of xy equal to c. So we have the following problem. I can write it in a more clear way. The objective is to maximize or minimize f of xy subject to the constraint g of xy equal to c. Okay, so this is our objective in constraint optimization. You can clearly see it's a simple optimization problem. Objective function is f as a function of x and y. Okay, this is my objective function. And g of xy equal to c is my constraint. Okay, it's the constraint which is holding true at the equality. G of xy exactly equal to c. Okay, so we can now write a necessary condition. A necessary condition for the pair x comma y to solve the above problem is f1 dash xy, which is nothing but the partial derivative of the function f of xy with respect to x, upon f2 dash xy, which is the partial derivative of the function f with respect to y, should exactly be equal to g1 dash xy, which is the partial derivative of the function g with respect to x, divided by g2 dash xy, which is the partial derivative of the function g with respect to y. So this is my necessary condition for solving the above optimization problem subject to an equality constraint. So I'm quickly revising this with all the students. Okay, we are dealing with optimization problem involving two variables x and y and one equality constraint. Objective is to maximize or minimize the objective function, which is f of xy, subject to the constraint which is g of xy equal to c. The necessary condition which is going to solve this optimization problem is that pair of x comma y which satisfies this condition. f1 dash xy upon f2 dash xy is equal to g1 dash xy upon g2 dash xy. Okay, let's now practice a few questions based on this. Let's practice a few questions. So question 1. Find the only possible solution. Find the only possible solution to the problem, which is as follows. Maximize xy subject to 2x plus y equal to m, where m is a constant. Okay, m is a constant. So let's quickly do the optimization for this particular question. So clearly all students can see my objective function is f of xy, which is nothing but x into y, and my constraint is g of xy equal to c. So my g of xy is what? My g of xy is 2x plus y. If you compare the problem given to us in the question with the general optimization problem, maximize f of xy subject to g of xy equal to c. Clearly you can see f of xy is x into y, g of xy is 2x plus y. So if I apply the necessary condition we have just learned, what is the necessary condition? The necessary condition is f1 dash xy upon f2 dash xy is equal to g1 dash xy upon g2 dash xy, which implies what is f1 dash xy? If I differentiate the function with respect to x, I get y. If I differentiate the function with respect to y, I get x equals, if I differentiate my function g with respect to x, I get 2. If I differentiate my function g with respect to y, I get 1. So y by x is equal to 2 by 1, which implies y is equal to 2 times x. Now I'm going to put it in the constraint. So I can write putting y equal to 2x in the constraint. What do I get, guys? 2x plus y. Now what is y? Y itself is nothing but 2x equals m, which implies 4x is equal to m, which implies my x star is equal to m by 4. And once I have found out x star, I can find out y star. Y star is equal to 2x star, which is 2 times m by 4, which is m by 4. So clearly all students can see that for this particular optimization problem, we get the equilibrium values or the optimum values, which are x star equal to m by 4 and y star equal to m by 2. Okay, and you multiply them, you get the maximum value of the function. So I can write f of x star y star will be x star into y star, which is nothing but m by 4 multiplied by m by 2, which is m square by 8. The maximum value of the function f of x star y star is nothing but m by 4 multiplied by m by 2, which is m square by 8. Okay, so let's look at the next question for practice. Question 2. Find the possible solution. Find the possible solution. Okay, to the consumer demand problem. We need to find the possible solution to the consumer demand problem. The demand problem is as follows: maximize utility, which is x to the power alpha, y to the power beta. Clearly, it's a Cobb-Douglas function, Cobb-Douglas utility function. Okay, in microeconomics, subject to the budget constraint px plus y equal to m. where alpha and beta are positive constants. Okay, where alpha and beta are positive constants. Okay, so let's quickly solve up this question. So again, all students can clearly see, if I look at f of xy, which is my objective function, it's nothing but x to the power alpha, y to the power beta. If I look at my constraint function g of xy, it's nothing but px plus y. What is my necessary condition? Therefore, the necessary condition is for the above maximization problem. The necessary condition for the above maximization problem is f1 dash xy upon f2 dash xy equals g1 dash xy divided by g2 dash xy. Okay, so this is our necessary condition. What is f1 dash xy? Differentiate with respect to x. Alpha x to the power alpha minus 1 y to the power beta upon differentiate with respect to y. So we get beta x to the power alpha y to the power beta minus 1 equals g1 dash. If I differentiate this with respect to x, I get p. If I differentiate with respect to y, I get 1. So this implies alpha by beta times y by x is equal to p. Okay, so I can write this implies alpha y by beta is equal to px. I can take x to the right hand side. I get alpha y by beta equals px. Now, if I put this in the constraint, putting this in the constraint, let us see what do we get. Okay, so we have px. Now, what is px? Alpha y by beta. Okay, our px, I can, let me do it on the top. Let me erase the initial part now. Let me solve this question further on the top. So my px is nothing but alpha y by beta from this equation plus y equals m. I can take y common on the left hand side, so I get alpha plus beta by beta equals m. My y star comes out as beta upon alpha plus beta times m. Okay, and if I plug this value now in the equation for x star, I can get the required value of x star. So what I'm doing is I'm erasing this particular part, and then we can quickly find out x star. Okay, erasing this particular part, we can now find out optimum value of x star. So my x star will be, or I can write px star is equal to alpha y star by beta. This implies my x star is nothing but alpha by beta p times y star. Okay. Now, what is y star? You can plug in the value. So, alpha by beta p times, put the value of y star, which is beta upon alpha plus beta m. Okay. So, what do I get as my answer? Beta beta cancels. I get alpha upon alpha m upon alpha plus beta times p. This is my optimum value of x star. Okay, so hoping students have understood this. For this particular problem, you can clearly see my x star and y star are as follows. X star is alpha upon alpha plus beta times m by p, and y star is beta upon alpha plus beta times m. If we write the interpretation, you can even interpret this, since it was the optimization problem for the consumer in microeconomics, where the objective is to maximize utility subject to the budget constraint. If you clearly see, guys, this was your utility function and this was your budget constraint. Okay, so if I interpret the results, I can even interpret them. The consumer, in order to maximize his utility, should spend the fraction alpha upon alpha plus beta, should spend the fraction alpha upon alpha plus beta of the income on the first good, or I can write on good X, and the fraction beta upon alpha by beta of its income on good Y. Okay, so all students can clearly look at the interpretation, look at the way we have interpreted our results. In order to maximize the given utility function subject to the budget constraint, the consumer should spend alpha upon alpha plus beta of its income on good X and beta upon alpha plus beta of its income on good Y. Okay, so hoping all students have understood this. Let us practice one more question. Question 3. Again, the objective is to maximize or minimize the function 3xy subject to x square plus y square equals 8. Okay, so clearly all students can see my function f of xy is 3xy. My function g of xy is equal to x square plus y square. What is the necessary condition? The necessary condition is f1 dash xy upon f2 dash xy exactly equals g1 dash xy upon g2 dash xy. What is f1 dash xy? 3y. What is f2 dash xy? 3x. What is g1 dash xy? 2x. g2 dash xy? 2y. So this implies y by x is equal to x by y, which implies y square equals x square. Now y square equal to x square, we can put this in the constraint. What is the constraint, guys? X square plus y square equal to 8. So x square plus y square is also x square equal to 8, which implies 2x square equals 8, which implies x square is equal to 4, which implies x is equal to plus minus. Okay, so what are the possible solutions? I can write if x is equal to plus 2, then y square will be equal to 4, which implies y will again be equal to plus 2 or minus 2. That means for this my possible solutions are 2 comma 2 and 2 comma minus 2. Because x is plus 2, for x equal to plus 2 you get y as plus minus. Okay, and another case is if x is equal to minus 2, in this case also my y square will be 4, which implies y will be plus minus 2. So my possible solutions are minus 2, 2 and minus 2 comma minus 2. Okay, now we have got all the points. We need to just plug them in the function. So I can erase the initial part. All I have to do is to plug in these values in the function. Okay, so I erase this particular part. We are going to plug the values in the function. So our function is what? F of xy. Our function is f of xy. And so let me make the proper table. We are going to plug the values of x comma y, and we are going to evaluate the function f of xy at these points. What are the points, guys, which we have got? The points we have got are 2 comma 2, 2 comma minus 2, minus 2 comma 2, minus 2 comma minus 2. So I am going to plug all these points in my function f of xy equal to 3xy. So all students can see, if I put 2 comma 2, I get 3 into 2 into 2, which is 12. And if I put minus 2 comma minus 2, then also I get the same value. Minus 2 will also give me the same value of f of xy, which is 12. If I put 2 comma minus 2, I get 3 into 2 into minus 2, which is minus 12. If I put minus 2 comma 2, I get 3 into minus 2 into 2, which is minus 12. Clearly, all students can see that the function has a maxima at 2 comma 2 and minus 2 comma minus 2. Okay, the function has a maxima. I can write this is my maximum value. This is my maximum value. So clearly all students can see the maximum value of the function is 12, which occurs at 2 comma 2 and minus 2 comma minus 2. And the function has the minimum value at these two particular points. So this also gives you the minimum value, which is minus 12. This also gives you the minimum value, which is minus 12. And this minimum value is happening at f x comma y, taking the value 2 comma minus 2 and minus 2 comma 2. So hoping all students have understood this particular question. Okay, now this was one particular way of solving the constraint optimization problem. Okay, let's now look at the next particular method, which we call as the Lagrangian method. Lagrangian method to solve the following problem. Lagrangian method. This is another method we use to solve constraint optimization problems. Again, first of all, I can write the simple two variable one equality constraint optimization problem, which is either maximize or minimize f of xy subject to the equality constraint g of xy equal to c. Now, one method we had done was to use the necessary condition. f1 dash xy upon f2 dash xy equals g1 dash xy upon g2 dash xy. Another method which all students can see on your screen is the Lagrangian method. So let's look at the steps involved in this method. Step number 1. Write down the Lagrangian function. Write down the Lagrangian function, which is L of xy equals my objective function f of xy plus lambda times the constant c minus the constraint function g of xy. This is my step number 1 towards solving the optimization problem using the Lagrangian method. You simply define the Lagrange function, okay, where lambda is a constant. Lambda is a constant. Actually, if you see, lambda is called the Lagrange multiplier. We will be discussing about this later in our lectures on constraint optimization. Okay, but right now students can write this, that lambda is nothing but the Lagrange multiplier. Okay, now step number 2. Once we have defined our Lagrange function, we are going to find out del L by del X and del L by del Y. Okay, and equate the partials equal to 0. That is, once we found out del L by del X, we are going to put it equal to 0. And once we find out del L by del Y, we are going to put it equal to 0. Okay, so what are the equations we will have? if I write del L by del X, this is my Lagrange function. So I can write del L by del X equal to 0 implies I get F1 dash XY minus lambda times G1 dash XY equal to 0. If I solve it further, what do I get? F1 dash XY is equal to lambda times G1 dash XY. Okay. Similarly, I am erasing the initial part now. We are going to partially differentiate the Lagrange with respect to y and plug it equal to 0. So step 3 is getting continued on the top of the screen. Step 3 gets continued. We find out del L by del Y, plug it equal to 0. How do I find out del L by del Y? It's F2 dash XY minus lambda times G2 dash XY equal to 0, which implies F2 dash XY is equal to lambda times G2 dash XY. This was my equation 1. This is my equation 2. This is my equation 2. Okay. And then our third equation is del L by del lambda equal to 0. You also differentiate the Lagrange with respect to the Lagrangian multiplier lambda. If you do that, you simply get back the constraint C minus G of xy equal to 0, which implies G of xy is equal to C. This is my third equation. So basically, guys, we get three equations. When we partially differentiate the Lagrangian with respect to x, y, and lambda, we get three equations. First equation is f1 dash xy equals lambda times g1 dash xy. Second equation is f2 dash xy is lambda g2 dash xy. Third equation is g of xy equal to c. Now comes the last step. We need to solve these three equations. Very simple. So if I write step number 4, step number 4 is solve the three equations for the three unknowns. What are the unknowns, guys? The unknowns are x, y, and lambda. So if I quickly revise the steps, okay. Again, the objective is to use the Lagrangian method to solve the simple two-variable constraint optimization problem subject to an equality constraint. Step number 1, you define the Lagrange, which is f of xy plus lambda times c minus g of xy, where lambda is a constant, also called the Lagrange multiplier. Step number 2, you find out del L by del x and del L by del y, equate them equal to 0. Step number 3, what are the equations you will be getting? Del L by del x equal to 0 will give you this equation. Del L by del y equal to 0 will give you this equation. Del L by del lambda equal to 0 will give you back the constraint itself. You have three equations, you have three unknowns, x, y, and lambda. I expect students by now to understand how to solve three equations and three unknowns. Very simple. Okay, so let's do a dummy question and then we are going to stop in this particular lecture. Let's look at a practice question based on Lagrangian method. Okay, so the question is as follows. Solve the following problem. Solve the following problem using the Lagrange method. Now this is as follows. Maximize or minimize f of xy equals x square plus y square subject to g of xy equals x square plus xy plus y square equals 3. Okay, so basically this is my g of xy and this is my c. Okay, so quickly we can define the Lagrangian. We define the Lagrange. We define the Lagrange function for the above problem as L of xy equals f of xy, which is x square plus y square, plus lambda times the constant is 3, minus g of xy, which is x square plus xy plus y square. Okay, now I can do one thing. I can remove this particular, okay, I can remove this particular bracket and I can put minus inside. Okay, so now our first order conditions, let's quickly solve them. Del L by del x equal to 0, which implies 2x plus lambda times minus 2x minus y equal to 0, which I can write as 2x is equal to lambda times 2x plus y. This is equation 1. I basically took this to the right hand side. Okay, then we have, similarly I can write my next first order condition, del L by del y equal to 0, which implies 2y plus lambda times minus x minus 2y equal to 0. Again, this whole term can be taken to the right hand side. We get 2y equals lambda times x plus 2y. This is nothing but equation number 2. Okay, so now we can divide equation 1 by equation 2. Equation 1 by equation 2 implies 2x by 2y equals lambda times 2x plus y upon lambda times x plus 2y. 2 cancels, lambda lambda cancels. I can cross multiply x times x plus 2y equals y times 2x plus y, which implies x square plus 2xy is equal to 2xy plus y square. We get x square equal to y square. Okay, so now let us see what are we going to do. So x square equal to y square means what, guys? It means either x is equal to y or minus x is equal to y. When I write x square equal to y square, it means either x is equal to y or x minus x is equal to y. Okay, now my third condition is del L by del lambda equal to 0, right? If I differentiate del L by del lambda equal to 0, I simply get the constraint back, x square plus xy plus y square equal to 2. Now in this particular constraint, I am going to put x equal to y and minus x equal to y. Okay, so I erase the initial part. Now let's work this out further. So I can write case 1. If I take the case that x is equal to y, so putting this in the constraint, putting this in the constraint, what do I get? X square plus x into y is nothing but x only, plus y is again x. This is equal to 3. So 3 times x square is equal to 3, which implies x square is 1, which implies x is equal to plus minus 1. And if x is equal to plus minus 1, I can write y is also equal to plus minus 1 because x is equal to y. Okay, so this is one possible solution I have. So now basically it's giving me the following solution. When x is 1, y is 1. When x is minus 1, y is minus 1. Now I need to solve for lambda also. Okay, so I can find the value of lambda from equation 1. So all students can see this. Suppose I take 1 comma 1. Suppose x and y both are equal to 1. Okay, suppose x and y both are equal to 1, then how can I solve this? So I can write, therefore if I use this equation, guys, 2x is equal to lambda times 2x plus y. I can use this equation. Okay, so I am erasing this particular part. Let's solve this up further. I'm erasing the first order conditions now. Okay, so in this in this particular equation, if I put 1 comma 1, so 2 into 1 is lambda times 2 plus 1, which implies 2 is equal to 3 lambda, which implies lambda is equal to 2 by 3. And if I put minus 1 comma minus 1 in this equation, 2 into minus 1 is lambda times minus 2 minus 1, which implies minus 2 is equal to minus 3 lambda, which implies lambda is again 2 by 3. In both the cases, I get lambda as 2 by 3. So I can say for case 1, my x star, y star, and lambda star are 1, 1, 2 by 3. And another possible solution is minus 1, minus 1, 2 by 3. Either my x and y can be 1, 1, in which case lambda is 2 by 3, or my x and y can be minus 1, minus 1, in which case also my lambda is 2 by 3. Okay, then let's look at the second case. What was the second case? Minus x equal to y. So I'm erasing the bottom portion now. Let's evaluate case 2. Okay, erasing all this off. Let's evaluate case 2. So I can now write for case 2, we have minus x equal to y. Now, if I put this in the constraint, let us see what do I get. So putting this in the constraint, okay, so I get x square plus x into y, which is minus x, plus y is minus x square equal to 3, which implies x square minus x square plus x square equals 3, which implies I get x as plus minus root 3. So clearly, if x is equal to plus root 3, y is equal to minus root 3, I can find the value of lambda, guys, if I plug it in this equation. So I can write 2x is equal to lambda times 2x plus y, which implies 2 root 3 is equal to lambda times 2 root 3 minus root 3, which implies 2 root 3 is equal to root 3 times lambda, which implies lambda is 2. And on the other hand, if I take x as minus root 3, because x is plus minus root 3, right? So if I take x as minus root 3, then y will be plus root 3. In which case, again, if I put it in this particular function and solve it for lambda, again, you can see that you will get the value of lambda as 2. You put x as minus root 3 and you put y as plus root 3 in this equation, you can again verify that you get lambda as 2. That means for case 2, we are getting another possible solution. So what is the solution for case 2? If I erase the initial part, I'm erasing the question now. We have found out the solution. Okay, so for case 2, my optimum solution x star, y star, lambda star is either plus root 3 minus root 3 2, or I can say another possible solution we can have is x star is minus root 3, y star is plus root 3, and lambda is again 2. Okay, so these are the values I get. So now, guys, my objective is to evaluate the function f of xy at these points to find out the maxima or the minima. Remember, the question is not over yet. We have found out all the possible points. Now we need to check when is the function maximum or minimum. So I erase this whole part now. I erase this whole part now, and we are going to evaluate the function. Okay, so if all of you can recall, our function was x square plus y square. That was our objective function for this problem. Okay, so let us look at this. We have the points and we have f of xy. Okay, we have f of xy, which is x square plus y square. Now I can put all the points. My points are 1 comma 1, minus 1 comma minus 1. Okay, then we have plus root 3 comma minus root 3. Then we have minus root 3 comma plus root 3. These are all possible pairs of x comma y, which we have got. I plug them in the function. So 1 square plus 1 square is 2. Minus 1 square plus minus 1 square is also 2. Root 3 ka square plus minus root 3 ka square is 6. Okay. And then again minus root 3 ka square plus root 3 ka square is also 6. So all students can see that the function has the maximum value at plus root 3 minus root 3 and minus root 3 plus root 3. The maximum value of the function is 6, which occurs at these points. And if you look at the minimum value of the function is 2. I can say the function has minimum value at 2, and this occurs at the points 1 comma 1 and minus 1 comma minus 1. So hoping all students have understood this particular problem where we have used the Lagrangian method to solve for the optimum values. Okay, so students, this is where I intend to stop in this particular lecture. The objective was to discuss with all students the simple constraint optimization problem involving the objective function in two variables x and y and one constraint g of xy exactly equal to c. This is the equality constraint. We looked at two ways in this lecture to solve. One method was to use the necessary condition, which was f1 dash xy divided by f2 dash xy equals g1 dash xy divided by g2 dash xy. Another method is the Lagrange method. Okay, for both these methods we have done good practice. So now in the next lecture of constraint optimization, I will be talking more about Lagrange multiplier. Remember, in this lecture we said that lambda is called the Lagrange multiplier. Now in the next lecture we will see what is the economic interpretation. How do you interpret the Lagrange multiplier? That is something which we are going to see in the next lecture of constraint optimization. So I hope all students have enjoyed this lecture. Any doubt, you can unmute your mics and ask, or call up or mail me your doubts at divineschoolofeconomics@gmail.com. So this is where I stop in this lecture.